So good afternoon and welcome to the lecture today. We're in week 5 now, which means we're halfway of the course. And as you know, later this week there is going to be the midterm. And you should have received an email from the calculus team by now about the organization of the midterm. If not, please check with your fellow students, and otherwise send an email to calculusabc@tue.nl, the general organizational team behind the course for all 3,000 first year students. So I hope you're all well and that you're up for the lectures. So the topic this week is going to be about exponential and logarithmic functions. And I promise you one thing, if you think about exponential functions, probably you know the term exponential growth. We hear a lot about that due to coronavirus. I'm not going to be talking about the virus. I mean, I think you hear enough about it, so I won't take that as an application this week. Before I go to the week 5 material, let me first go through the questions that you have posted on Canvas. So I'm going to switch to the Canvas screen. Let's take this one. Yep, then we see everything. So question of the week. If you ever wonder about the B, that's because there is a time slot A, time slot B, time slot A, that's our friend from architecture, time slot B, that's us, industrial design. And there have been a couple of questions in the meantime. So the first one is, could you please explain again how you would calculate the cosine of the arctangent of x? So last week we talked about the inverse sine, inverse cosine, inverse tangent functions, arcsine, arccosine, arctangent. And we have seen how you can sometimes simplify expressions with this. So I gave one example during the lecture, and you can go back and check that. And here's one more example. So the way you would do that, so I'm not going to do it in every detail, but let me switch to my iPad. That should be here. Yep, that's great. And let's get a new bit of virtual paper. So handwritten notes. So the question here on Canvas is to tell something about the cosine of the arctangent of x. So we have to rewrite this in a simpler form. Now, I'm not going to do all the steps because that is basically what I've done during the lectures last week, but I would like to give the general idea how you would do this. So the idea is to call this phi. So then the whole expression reduces to being the cosine of phi. But the way I introduced phi here is that phi is apparently equal to the arctangent of x. And as we have seen, that means that the tangent of phi equals x. And now this is the part where you have to draw a little triangle and then use the rules with SOS cos TOA is the way you may have heard it. But basically, if we have something like this, then we can draw a triangle with an angle phi, a 90-degree angle. And then we know that the tangent is the length of the opposite side over the adjacent side. So if I rewrite this as x divided by 1, then I could call the length of the opposite side x, and the length of the adjacent side 1. And then we use Pythagoras. And Pythagoras tells us that this has length 1 plus x squared. And now what we need to do is read off the cosine, because the original question here is to give an expression for the cosine of phi. And I said I wasn't going to do the complete question, and maybe you would put in some more comments because this is just a notes and you have my additional speaking with it. But what we're being asked for now is the cosine of phi. So the cosine, as you know, is the length of the adjacent over the length of the long side. Now the adjacent side is length 1, and then the long side has length 1 plus x squared. So that is how you would do that. So you introduce a bit of new notation. You call the arctangent of x, you call that phi. And then you're going to use basically the definition that you just did. Oops, sorry about that. The definition you just had. You use the definition with the arc functions, the inverse functions. Draw a triangle, read of the answer. So that's the steps that you would do here. There's already a couple of questions on the midterm. I'll delay those. I'll first go through the questions on the canvas, and then I'll switch to the questions in the chat box later on. So let's see. That's the first one. So here it says how. Oh, sorry. I'll switch to this screen again. Then you see the same thing as I do. So it says here, how do you implicitly derive the function? And then I have a bit of trouble with the notation here, because what it says here is the function fx is, and then a complicated expression. But as you see, this is not quite correct, right? Because we have not a function of x, but if you would like to call this a function, it would be a function of x and y. But we really do not have a function here. What we basically have is a curve. So we have this x over y squared plus 2y to the power 3 equals 1. If you would look at all points x, y that satisfy this equation, so if you take an x value, y value, you plug it into the equation and it fits there, then we'll describe a curve in the plane. So I haven't got a clue what that curve looks like, but it is going to be something like this. So let me switch to my iPad again. So we have the equation x over y squared plus 2y to the power 3 equals 1. So this is not a function, it's a curve. It describes a curve in the plane. So if you have x-axis, y-axis, then if you would look at the points, then you would get some shape. I haven't got a clue what it looks like, so I'm just drawing something, but you have a curve C. So you label the points x and y to satisfy the equation, and that gives a curve. Now, if you would have to differentiate this thing, well, as we have seen last time, what you could try to do is solve y as a function of x and then differentiate. But it's likely not going to work here because we have a rather complicated expression and there is a y to the power 3. That's not going to work here. So what we do is we're going to use implicit differentiation. So let's answer it here, implicit differentiation. So what I'm going to do is I'm going to assume that y is a function of x. Assume y equals f of x. And I'm going to substitute that into the equation. So then we have x over fx squared plus 2 fx to the power 3 equals 1. And because I need to differentiate, I prefer to write this as x times fx to the power minus 2 plus 2 times f of x to the power 3 equals 1. And now I'm going to differentiate with respect to x. So if I differentiate x, I get 1. So I get fx to the power minus 2 plus x times, and then I have to differentiate this fx to the power minus 2. So I get minus 2 times fx to the power minus 3. And then with the chain rule, I have to differentiate f again. So f prime x. And that is the first term where I use the product rule. Plus 2 times 3 times fx to the power 2. And again with the chain rule, times f prime x equals, and then I have to differentiate 1. 1 is a constant. If you differentiate, you get 0. So this is how it would work. And now if you're being asked for f prime of x for a general formula, you could solve this for f prime x. But usually, if you have done a couple of these problems, usually you're being asked for a tangent line, and you would only have to know the derivative at one point, and then you just plug in the x and the y value and solve for f prime. So I'm going to stop here, but this is how you would do the differentiation. Okay. Let me switch to the website again. So how do you solve this question? The function f given by this thing is 1-to-1. Find the derivative of the inverse. So here the person asking already says, well, normally I would compute the inverse and then take the derivative. That's not going to work here. So this is something that we covered last week, and there is an example for that. But the basic idea, so I'm not going to do the full question here, but the basic idea is that if you have f g and f inverse is g, or g inverse equals f, then we have seen last time that if you use f g x equals x, so saying that they're each other's inverses, and you differentiate that, so I'm going to differentiate, and I get f prime gx times chain rule g prime x equals 1, and then we have g prime x equals 1 over f prime of gx. So here you see that without actually solving for the inverse function, you can still say something about the derivative. And we did an example last week. So for the person who has asked this, look at the example from last week and see if you understand that. If you still do not understand, ask again, and I'll do it more extensively on Wednesday. And indeed, I forgot to switch to my iPad. So let me quickly go through that. So we had f and g, and they're each other's inverses, as it says here. And then from the relation f gx equals x, if you differentiate that, you get a relation between g prime and f prime. But as I said, this is something that we covered last week, but you just have to know which sections you would have to look at. So for the person who has asked this question, check out that. And if you do not manage, I'll get back to it on Wednesday. So I'll just ask again then. Okie doke. Next question. I'm going to switch to the correct screen and hopefully switch back later. Could you explain how to calculate this? Consider the curve given by the equation x times y minus 3x plus 4y equals 2. Find the equation of the tangent in the point 1, 1. This is related to what we just did. So this is where you have to do implicit differentiation. You assume that y is a function of x, plug that into the equation, differentiate the whole equation, and in that way you can find the slope of the tangent curve. So this is something, implicit differentiation is the key word here. So try to do that again. If this is not enough as a hint, I'll happily come back to it. But for now, I'm leaving it here so you can try for yourself again. Can you explain the difference between parametric form, equation form, vector form, symmetric form from the book? That is not sufficiently clear here. You have to elaborate for this question. I don't understand what the question means. Maybe refer to the book and the page where this is covered in the book, because I do not get the question here. How do we need to write down the polar form of a line in the right way? So polar form is something for a vector. So as you may recall, and I am now going to recall to switch screens, a vector has a polar form. So if you have, let's see, if you have the xy plane and you have a vector, let's call this thing A, then you know that we can either specify this by giving basically the two components, coordinates of this vector. So A is the vector A1, A2. But alternatively, what you could also do is that you say, let's pick black here, that's clear, that you say, well, I know this length here, and this length I call little r, and then the angle with the positive horizontal axis I call theta. And then you could also give A by specifying r and theta. And r and theta are the polar coordinates. The book is not very clear about polar notation, but if you give the value of r, and as you see, r is basically the length of this vector, and theta is this angle. And as you can also see from the graph here, you see that the tangent of theta is the length of the opposite side, which would be A2, over the length of the adjacent side, which is A1. So r and theta, those are the polar coordinates. Yep. Okido, I'm going back to questions. Can you solve the fifth equation from the midterm 2019? I couldn't compute part B. I don't have the question here now, and looking it up is going to cost me too much time. I should think that the answers are provided. If not, I'll have a look and I'll come back either after the break or on Wednesday. So just let me write a note here, because otherwise I'm sure to forget with so many things. Midterm 2019. Industrial design 5B. Okay. I'll have a look. Could you show how to make a vector representation of a plane? Okay. I did it the other way around during the lectures. So given the vector equation, I gave the normal equation with some constant times x plus some constant times y plus some constant times z equals a constant again. To do it the other way around, what you have to do is you have to find two vectors that lie in the plane. So you can choose any two vectors as long as they point in different directions. So not one vector plus a multiple, but one vector plus something pointing in a different direction. You can use those as direction vectors, and then you have to pick one point in the plane. So to make that a little bit easier to understand, let me switch to my iPad. Okay, next page. So say that we have some plane, let's say we have a plane V, let's say 2x minus 3y plus z equals 10. I'm just making that up as we go. And what you would like to have is the vector equation. So that would be something like x, y, z equals, let's say a1, a2, a3 plus lambda times b1, b2, b3 plus mu c1, c2, c3. And now the picture that you should have in mind is that a plane in 3D is something like this. And because we have the equation here, we can find a normal. So reading off the coefficients here in this equation, I can find that a normal to the plane would be the vector and then the coefficient of x, which is 2, coefficient of y, which is minus 3, coefficient of z equals 1. This vector is orthogonal to the plane, makes a 90-degree angle with the plane. So n, and this is the plane V. Now, these vectors B and C here, they should lie in the plane, which means that B and C are vectors that lie in this plane. So it means that they are orthogonal to the normal. So you should pick, you can choose two vectors, B and C, different vectors that are orthogonal to the normal. And then finally we have this thing here. And basically what you have to do is you just have to pick any point in the plane, and then if you have a coordinate system, x, y, z, then for the vector A, you pick a vector that points from the origin to a point in the plane. How can you find such an A? That's not so difficult. You can just choose, well, let's say, so a point in V. So let's say that I choose x equals 1, y equals 1, and then I just use the equation of the plane, so this equation here, to compute the corresponding z value. So then you would find that z equals 10 minus 2x plus 3y. So I rewrote the equation for the plane, and you find 10 minus 2 plus 3 equals 11. So apparently for A I could pick 1, 1, 11. And then I have a point that lies in the plane. Okay? So these are a few pointers, not a complete solution, but this is how you can manage from the normal equation of a plane to get to the vector equation. And the other way around, we've done that during the lecture. So you can find that in the lectures for either week 2 or the beginning of week 3. I cannot really remember when I covered this, but I'm sure you can manage there. Okay, so let's see. I'm going to switch to the questions again. If the domain equals minus infinity up to minus 8, and then union 5 to infinity, is it fine to write it like this? If you add to that all x that satisfy this inequality, then it's okay. And if you would like to do that more mathematically, the way you would write that, let me switch. The way you would write that, so, oops, what did I do here? New page. So we have it's better. We have minus infinity up to minus 8 union 5 to infinity, and the alternative way to write that would be equals the set of all x in the real numbers for which, and then you get it's written a bit different here, but if I take it like this, x is less than minus 8 or x is bigger than 5. So that is how you could write that as a set. Okay. I'm switching back to the questions. Yep. So here is, for example 4.8, you're asked to determine the intervals where f is continuous. The function is fx square root 4 minus x squared. If 4 minus x squared is bigger than 0, f is continuous. Yeah, that's true. So that's the interval from minus 2 to plus 2, which I agree with. Good. And then they also say, yeah, we already talked about this a little bit, right? So the normal square root function, square root of x, is continuous for x positive, but also for x in 0. The book is not very clear on that, but the square root function is continuous at 0. And as a consequence, the function in this question is also continuous in minus 2 and plus 2. So that will be the answer here. So, but the book is not very clear about that. But the square root function, square root of x, is also continuous for x equals 0. So for x bigger equals 0, it is continuous. Okie doke. When writing a vector in polar form, you have to give theta and r. Yeah, that's correct. How you write that down, we already covered it a little bit. That is not that important. As long as you give the r value and the theta value, you're fine. And then the notation it's not standardized, and the book is also not clear about that. But providing r and theta, that is the polar form. Can you use the formulas and then trigonometric formulas immediately without deriving them? Yes, you can. So these kind of elementary trigonometric formulas, some standard form you get during the test, and you can look at the old test to see which formula sheets you get. The ones that you can derive from that trivially, by replacing alpha with minus alpha, whatever, you don't have to give the derivation for that. Note that sometimes it is good to write down the equation that you will be using in your solutions. Should you make a little mistake, then we know where it came from, and we can still give you partial points. So it is not, if you give an incorrect answer, that you score 0 points. If you make small computational error, you can still get partial points. Here, I find it very difficult to write a polynomial of degree 3 and higher as a product of 3 polynomials of degree 1. There is two ways. So if you have a polynomial of degree 3, there is not a simple standard formula for that, which means that you should be able to see one of the zeros easily. And then you can write your third degree polynomial as, say that 2 is a 0, as x minus 2 times something else. How you can find this something else, I gave an example there where you would write it as ax squared plus bx plus c and then try to solve for a, b and c. You can also do long division, but if you have never seen that, it's not really the effort to do it here. If you have seen that before, you can use long division, and otherwise you just have to do the multiplication, compare coefficients, do it like that. If you have a concrete example, if you give me a third degree polynomial and you don't manage how to do it, show me the polynomial and what you try to do, and I'll get back to it on Wednesday. Do you have to find the vertical asymptotes like in slide 40? Because I've always learned to make the denominator equal to 0. That is true. So vertical asymptotes appear where may appear where the denominator becomes 0. But if you want to know if they go to plus infinity or minus infinity, you have to do a little extra work. And that's what we did last week when we were talking about limits and limits going to plus and minus infinity. So if you would have to draw it, you would have to know if you go up or if you go down. So that's why I did that. And do we have to know the applications? No, you don't have to learn the applications, but the mathematics in the applications, that is the mathematics that we cover, so you have to do that. So I could ask for a question related to an application, but you don't have to learn these things by heart. So you do not have to know the secant, cotangent, etc. Just sine, cosine, and tangent functions. We won't be using the other ones. How do you calculate the values of an inverse sine, cosine, tangent? You can use the unit circle, that's true. So it would have to be nice angles. So if you know what the sine is of a certain angle, you also know it the other way around. So it's basically the rules that you already know for sine, cosine, and tangent, but then in opposite direction, basically. That's what we do there. Yep. And then here, to come back to my question about differentiation, do I understand correctly? So here, basically, how far do I need to simplify my result to come to an answer? It is going to be relatively easy in this test, since we will give you multiple choice options and then also ask for your solution. So you have to click an answer from multiple choice alternatives. So that immediately makes clear how far you should do the simplification or rewriting of your answer. It should be among the options in the multiple choice question. And then we also ask you for your solutions. So in a sense, you're being helped here a little bit, because if you make a small plus or minus error, then your answer would not be among the multiple choice options and you can check your result again. So that's even better than it was previously. Okay, so that concludes the questions here for now. So I'm going to start another round of questions again, and then we can cover those on Wednesday. So let's see, that was, I think, the plus sign here. Is that a new round? Yep, open a new round of questions. Okay. No questions, excellent. Okay, I'll switch to the chat box for now, since I'm answering questions, that maybe helps. Does the proctoring start automatically? You should have had information about the proctoring. There is videos on how that works, so try to find out. I think it's being linked in the email that you get, but there are introductory videos on how the proctoring works. So about the formula sheet, you will get it during the test. So you don't have to provide it yourself. We will give it to you. So it is available during the test to you. You have to switch screens, I know. We cannot see, I know. Is it possible to do the midterm test in the time slot of Bouwkunde? In principle, not. It's the same course, only if you have a very strict reason for it. Send an email to calculusabc@tue.nl. Maybe they will make an exception, but in principle you should take the test in the allotted time slot for you. About the time for uploading, that is being detailed. So I'm not going to say stuff about that now because I'm not exactly sure. If you have questions about that, send an email to calculusabc@tue.nl. But in principle, you will have sufficient time for answering, and then you will have additional time to do the uploading. But the details, ask calculusabc@tue.nl if it is not clear from the email and the extra information provided. Okay. So that covers the questions for now. Keep them coming. I'll look again in the break, but for now I'll switch to the week 5 material, and I'll ignore the questions for a little bit because otherwise I will go mad. So I'm going to switch to my iPad. Excellent. And let's have a little look at what we will be covering this week. So here you see the sections from the book, so a bit from chapter 0, chapter 2, and chapter 3. And what we will be working with, as I already said, is exponential functions, logarithmic functions. They're each other's inverses, as you hopefully recall. So it makes sense to cover them at the same time. And we have already seen what an inverse function is, so that's the way that we will introduce one of them, basically. We're going to differentiate them, and we will also be talking about linear approximations and L'Hopital. And we have got a couple of nice applications, as you may have seen, going through my answers. So on the title slide, maybe you have recognized this. This is some artwork that was created by Gaudí. So if you go to Barcelona, there is a lot of artwork from Gaudí, and La Sagrada Familia is still being constructed. That's not finished yet. But one of the things that Gaudí used in his art is basically mathematics. And that is that he used a shape that a free hanging chain, so if you have a bicycle, of course you do, because you live in the Netherlands, if you take a bicycle chain, so the lock that you have, the separate lock for your bicycle, and you keep it at the end points, it assumes a certain shape. And the shape it assumes is a cosine hyperbolic, so we will be talking about cosine hyperbolic functions. And that is a very strong construction. It looks a little bit like a parabola, but it is different from that. And you can use that to make constructions. And Gaudí used that a lot. So we will be talking about that, which is kind of nice. But before we get there, we first have to talk a little bit about the exponential function. Now, normally in a classroom, I would be showing this video. So this is James Grime. He's a British mathematician. And he gives popular talks about mathematics. And he does that in a very nice way, I think. Now, I'm not going to play the video, as I'm not completely sure how this is with copyrighted material and so on. And I don't want this video to be taken down. So if there would be copyrighted material in there, YouTube might take it down completely, and I don't want that. So I would urge you or ask you, or well, it is a fun video. The link is here on the slide. So if you click the link, if you have the PDF file from my slides, you can pick it up on Canvas. And if you click there, you get a YouTube video from James Grime. So it's a very nice video, I think. And basically what he talks about is an introduction to E, the Euler number. So as you may know, E is one of the mathematical constants. There's a couple of them. There's like pi, 3.14 and so on. There is the square root of 2, 1.41 and so on. And there is also E. And E is the number, so E is approximately 2.718. And then a lot more digits, and they do not repeat. So it's an irrational number. You cannot write it as a quotient. It is in the real numbers, but not in the set Q. If you remember from our first week, we had Q and we had R as sets of numbers. Now, the way that he introduces it is, well, not by means of geometric construction. So if you think about pi, you can draw a circle and then you know that the circumference, that's related to pi. The square root of 2, if you would draw a square with sides 1, then the diagonal has length square root of 2. For E, this is not going to work. So to introduce E, what you could look at is something that Bernoulli worked on. Bernoulli is a mathematician from many, many years ago, hundreds of years ago. And the way he introduces it is, say that you have some savings and that you put €1 in the bank. And this bank is an exceptionally wealthy bank because they give you 100% interest per year. So interest per year, which means that after 1 year you would have €2. Now, as a kind of thought experiment, you could think what happens if you do not get your 100% interest after 1 year, but you say, well, I would like to have 50% interest after 6 months. So after 6 months you would be getting 150. And then you get another additional 50% interest after an additional 6 months. So then you would get €2.25. And you can repeat that. Say that we are not going to pay interest per half year, but per month. So this is option 1, this is option 2, and option 3 would be that you get, well, 1/12 interest per month. Then if you do that 12 times, and we are 1 year further, then you would be getting €2.61. So you see that if you pay a fraction of the interest, but multiple times, it goes up. And of course, you could also say, well, let's do it per week. So 1/52 per week. And that's 52 times, so then a full year. And if you compute it, then you would get €2.69. And you can probably imagine, you can do that per day, per hour, per minute, per second, or even continuously. So all the time you're getting interest and a fraction of that interest. Now, if you would look at that limit, it's a limit process, right? We let the delta t, the time lapse, we let it go to 0. Then it would go to the number E. That's what you would be getting. So that is something that Bernoulli figured out, but he didn't know the value yet. So he didn't know what it was, just that it was in between 2 and 3. And then Euler, one of the greatest mathematicians of all times, he worked it out and he found the value of E 2.718 and more digits like that. In the video, which is still interesting to watch, even though I'm spoiling a lot of it, they also give the formula e to the power I pi plus 1 equals 0. And in this formula, there is our number e, there is pi, there is 1, there is 0, and there is I, and I, maybe you heard about that, that's complex number. So basically we have, I'm going to write it like this because then it's going to disappear again, I squared equals -1. You can never do that with the real numbers, but there is complex numbers in mathematicians too. You don't have to know that for now, but this formula here is often chosen to be one of the most beautiful formulas in mathematics because it combines the 5 fundamental constants, numbers in mathematics. So that's also in the video. There is more detail on that in the video. Now, before we have a little coffee break, an application. So where do you use exponential functions? Because we will be talking about exponential functions. The constant e is related to growth in mathematics. And growth in the sense that we have a certain quantity and then it's multiplied by a fixed number, and we have a new quantity multiplied by a fixed number, new quantity, and so on. And it is typically used in applications when you have large variations in scale. So as it says here, if you think about sound, we already talked about that, that is pressure waves in air, and there is huge differences there. So your ear is responds to fluctuations as small as 10 to the power minus 9 times the normal atmospheric pressure. And the pain threshold, so when it really starts hurting, where you have really loud noise, is 10 to the power 6. And if you have those great differences in scale, you typically use logarithmic scales. So for sound, there is a kind of reference level, P0, that could be atmospheric pressure. And then if you have a certain pressure wave, a certain sound level, you do P over P0, and then you take a logarithm, the 10 logarithm, and you multiply. And this constant is just to get nice numbers. So basically the sound levels that we normally work with, you get nice numbers if you multiply with 20. And here you see a little table where you see different sound levels. If you have something like an Apple Watch, you know that it also keeps track of the sound levels around you. And then you typically see these types of values for different noises, different sounds. Other applications that you may know is the Richter scale for earthquakes. So if you measure the impact or how heavy an earthquake was. The pH scale for acids. So water is like neutral, and then you have acids and you have bases. Or the aperture on a camera, the f-stops. That's also a logarithmic scale that we have there. This is a little bit of an introduction to exponential functions and logarithms, and we will be talking more about that, but let's first have a little break and we'll continue at 2:30. So we have a break now, and I'll see you in 15 minutes. So let's start again. Before the break, there was a question about the midterm, an old midterm. And I just wanted to point out to you that if you go to the Canvas site, and it looks a little bit distorted here because I had to make it smaller to fit into the video footage. But if you go here and then if you go to the section on study materials here, like this, then you see that we have put up a couple of old midterm questions. So you see here the midterm test from 2019-2020, so last year and the year before that. And if you go down, it is for both AUBS, which is architecture and lots of other stuff, but basically bouwkunde, plus industrial design. And there is both the test and answers to the test. So if you want to practice for the midterm, this is where you can get the old test, and then you have got a pretty good idea about the type of questions we will be asking you on Thursday too. So there are answers provided there. If you still do not understand or have further questions, let me know, right? So I am going to do the same routine as I started with today. So I'm going to look at which questions you posted on Canvas. And I will cover those on Wednesday too. So if you have additional questions about the midterm, then the mathematical content, not the organizational bit. For the organizational bit, you're better off sending an email to calculusabc@tue.nl. But if you have questions about the mathematical content, then I'm happy to talk about that also on Wednesday morning. Okay, so that's what I wanted to show. Now let's go back to the slides, because we only just started with the topics for this week, for week 5. And as I said, we will be talking, well, first about exponential functions. And exponential functions are related to powers. And here's just a very quick recap of some of the rules. If you cannot really remember these rules, that's pretty much okay. Just take simple examples. So like I did here, if you don't work with these relations all the time, then you're likely to forget them because, well, you just need to work with them to remember them. So if you have something like 2 to the power 2 times 2 to the power 3, that's 4 times 8, which is 32, which is 2 to the power 5. And then you see that you can simply add this 2 and 3 to get this 5 here. And then the general rule is a to the power p times a to the power q is a to the power p plus q. So this general formula, well, you shouldn't learn it by heart. It's just like if you are solving a question, then you should be able to use the rule. And this is basically what you should remember, or what you should write on a scratch paper if you're not sure what the rule is. So similarly, if you have 2 times 5 to the power 3, on the one hand, that is 2 times 5 is 10 to the power 3, which is 1000. On the other hand, it's 2 to the power 3 times 5 to the power 3. So what it says here, this is 8 times 125, which is also 1000. So general rule, if you have ab to the power p, you can move the exponent p to the individual factors here. Got a few more of those. 1 over 2 to the power 3, that's 1 over 8, and that's the same as 2 to the power minus 3. So the general rule is 1 over a to the power n is a to the power minus n. The square root of 2 to the power 6, that's 2 to the power 3. Or in other words, the square root of 64 equals 8. That's basically what it says. But what it means is that if you take the square root, it's basically to the power 1/2. Okay. Next, 2 to the power 3 over 2 to the power 4. That's 2 to the power 3 times 2 to the power minus 4 is 2 to the power minus 1. Or if you like, 8 over 16 is 1/2. And in the formula, if you have this here, a to the power p over a to the power q, that's a to the power p minus q. We're almost there. The cubic root, that is to the power 1/3. So 15 over 3 equals 5. So if you have a to the power q and you would like to take the pth root, that is the same as to the power 1 over p. And then finally, I think 2 to the power 2, so that's 4 to the power 3. That's 4 times 4 times 4. That's 2 to the power 6. So what you could also do, and that makes it a bit shorter, is p times q. And then really the last one, square root of 2 times square root of 3. That's the square root of 2 times 3. So in a formula, square root of ab is square root a square root b, provided a and b are positive numbers. That's what I started with here. So if you're not entirely sure about these things, they are in this PDF Algebraic Skills, which is on Canvas in study materials. And there is also some questions about them, some assignments if you would like to practice with them. Now let's talk about the exponential function. So first, unexponential functions, there's more of them. If you have a function of this type, a times b to the power x, with a and b constants and b a positive number, this is called an exponential function and b is called the base. So for instance, here you have the graph of y is 2 to the power x. And if you want to draw that, you just plug in values for x, right? So 2 to the power 0 equals 1, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power minus 2 is 1 over 4, and so on. So you can easily plot that and you will see that it goes like this. So it crosses the vertical axis at 1, and it goes to 0 if you let x go to minus infinity, and for x to plus infinity, it also goes to infinity. Okay? Now, if you change this 2 to a 3 here, then what you see happening is that it will go up faster, like this. So you see that it's a bit, the blue is a bit below the red graph here, and it's above the red graph over there. And if you make it even bigger to 4, you see the same behavior. It goes up faster because 4 to the power 2 is 16 and 2 to the power 2 is only 4. So a bit of properties that we easily see from these graphs. You see that it has a horizontal asymptote y equals 0 for x going to minus infinity. It crosses the axis at 1, all of them do. They go to infinity. They are positive and they're increasing. So we looked at decreasing, increasing, and here you see that it goes up all the time. Now, if you have something like a half to the power x, so on the previous slides we took 2, 3, and 4, so always base numbers that are bigger than 1. If it is smaller than 1, then you can rewrite it. So that's 2 to the power minus x. And as such, if you would plot it, then here is the pictures we had before. And if you take b less than 1, then you just mirror in the y-axis. Because if you look here, then we get 2 to the power minus x. That is the mirror image of 2 to the power x in the y-axis. So just mirroring like that. Now, a bit more interesting is the slope of the tangent line. And this is an animation, so that doesn't work in this PDF viewer, so I have to go to this program here. So what you see here in the animation is that I should be able to write on this too, I guess. Can I? I can. So it's an animation and you see the b value, so the base of the exponential function. It is being varied here. So it is being varied in between 1.5 and for the maximum I think it goes up to 3. And you see if b is going up, then this graph is going to increase faster. And the black dashed line here, that is the tangent line at x equals 0. Now, the m that you see in the picture, that is the slope of the tangent line. And you see that the slope of the tangent line is close to 1. And for a certain value of b, it will be exactly 1. Now, that value of b for which the tangent line has exactly slope 1, we call that E, Euler's number. So let's see. So Euler's number is the unique number E such that M, the tangent line, has slope 1. And if you would compute that, you would find that it's 2.718 and so on. What you can also show that is not clear from this picture, but I put it on this slide because this is about the definition of Euler's number, is that it's also equal to this limit that you see here. It's a bit of a strange limit. Maybe you recall the interest rates that I was talking about before the break. Now, this is quite related to that. So to see that, let me go back to this slide here. And if you think back about the interest rate, then I said, for instance, that you have €1, and then in 1 month, you would be adding 1/12 of interest. And then if you would be getting interest of the bank of 1/12 and then every month, so 12 times, then your original euro would be multiplied with this number. And if you increase how often you do that, so if you do it per week, day, hour, and so on, you get something like this. And the n is then basically the number of time periods that you use. So if you let that go to infinity, then you would also be getting this number 2.718. So that is the relation between the introductory video that I still encourage you to see and this limit that you see here. Now, before I go to the next slide, I want you to consider this limit a little bit closer, because it shows you one thing. It shows you that you cannot take limits partly here. If you would just take the limit of 1 plus 1 over n, for n going to infinity, you would find 1 plus 0 is 1. Here you still raise the exponent, so it would be tempting to say, well, I'm first going to take the limit here in between the brackets and find 1, and then 1 to the power n, whichever n you give me, it always gives 1. It doesn't work like that. So you should take this at the same time here, and you will see that if you would compute this on a computer, that if you take bigger n, that you would actually be approaching this value here. Now, a little bit extra. What we have seen before is that functions that are 1 to 1 have an inverse. b to the power x is an increasing function if b is bigger than 1. And it's decreasing for b smaller than 1, but they're related, right? It's not very interesting to talk about those two cases all the time. So let's say that we have the increasing case. So the function is 1 to 1 on the full domain, which is every real number, so it has an inverse. And that inverse, that's called a logarithm. So logarithm, let b be the base, unequal to 1, because otherwise we have a very boring function. So y is b log of x is the same as x is b to the power y. You see b to the power y is always positive. So apparently the logarithm is defined for x bigger than 0 only, otherwise we cannot get an inverse there. Common choices are 2, e, the Euler number. And if we have the logarithm with base e, we write ln, and ln is the standard function we like to use for logarithms. And why I will make clear in a second. And 10 is often used in engineering, and that's also what is used in the past a lot. So if you have a textbook, you should always be a little bit careful, because if they just write log of x, then they often mean the 10 log, especially older textbooks. We will be very clear about that in the exam. In the exam, you will mostly encounter the natural logarithm, because that is the one that is most commonly used in mathematics and gives the easiest formulas. And the base, well, sometimes you see the little b up here and sometimes you see it down here. So both superscript and subscript are being used for that. Okay. So if we look at the natural logarithm that corresponds to e to the power x, with e the Euler number, we have seen that you can find the graph if you mirror in y equals x. Well, we have already seen that y is e to the power x goes like this. So if you mirror that, then you get the logarithm that you already know, of course, that you already have seen before. So we have that ln e to the power x equals x for every single number, because you can always compute e to the power x. And the other way around, e to the power ln x also is x, but here, since we write down ln x, that's only defined for positive x, so that holds for positive x only. Okay. Now, the book already asks a couple of questions about logarithms and exponentials, etc. So just as a little example how you can work with that, basically using that they're each other's inverses. So in the book is, I think it's from the book, the question solve ln x plus 5 equals 3. So we are being asked for which x value does this hold. So what you have to do here, we want to free the x, we want to solve for x. So I'm going to take the exponential on both sides of the equation, because then I can get rid of the ln. So if you do that, then you get e to the power ln x plus 5 equals e to the power 3. So that's something like 2.718 times 2.718 times 2.718. E and ln cancel. So what we find is that x plus 5 should equal e to the power 3. And in other words, we find that x equals e to the power 3 minus 5. So this is how you can solve these types of equations with logarithms or exponential functions. Basically, you have to use that they're each other's inverses. Okay. So one thing more. This is the graph of the natural logarithm. Now, if you change the base number, so the natural logarithm here in red, that equals the logarithm with base number e. We normally don't write that, we always write ln, but I just want to make clear for you that where it says e here, and if you make that a 10, then it will still have the same shape. It will also go through this point x equals 1, y equals 0, but it will go to infinity here a bit slower. So you see that it's below, the blue graph is below the red graph. If on the other hand you make it smaller, so 2, that's smaller than e, because e is 2.718, you see that it goes faster to infinity. And in general, what you have, you see that you have a vertical asymptote for x going to 0 from the right, from above. f1 equals 0, that holds for all these logarithms. It goes to infinity, but very slowly, and it's increasing. Like before, you can mirror again. If you would take a logarithm with a base less than 1, then you can rewrite it a little bit. It's not very interesting, because we normally always take the natural logarithm, but just so you know, if you have that y is the b log of x, then x is b to the power y. You can rewrite that as 1 over b to the power minus y. So what you see here basically is that if you have the log with base 1 over b, it's minus the log with base b. What does that mean? It means that you mirror the graph in the horizontal axis, as you see in the picture here. So here is the natural logarithm, and here is the log with base 1 over e. Here is the logarithm with 10, and here it's with 1 over 10. So if you have a base less than 1, it goes down apparently. Not particularly interesting or relevant. What is very interesting is the following property. So why did people invent logarithms? I mean, exponentials are quite clear, right? Because if you talk about growth processes like money and interest, although the interest rates are quite low these days, if you talk about bacterial growth, or if you talk about decay, like nuclear waste, it decays exponentially, there you can imagine why that holds true. Now, the main reason for inventing logarithms is the following. First, let's look at this little example here. So I wrote down 10 to the power 3, that's 1,000, times 10 to the power 5, that's 100,000. That's 10 to the power 8, right? That's a 1 with 8 zeros behind it. Now, if you use logarithms, and if you would use base 10 here, that makes sense because then it gets a lot easier. Then basically what it says here is that we have 3, 5, and 8. And you immediately see that 3 plus 5 equals 8. So apparently we have that the 10 log of 10 to the power 3 times 10 to the power 5 is the 10 log of 10 to the power 3 plus the 10 log of 10 to the power 5. Now, why is that interesting? This is not interesting yet because this is trivial. But if you take two arbitrary numbers, say x and y, and let's take them positive, and say that we want to multiply them, and they're quite big numbers. As you know, if you have to multiply two big numbers, if say they're integers, then you have to write them below and you have to multiply one by one and add all these in-between results together. That's a lot of work and you can easily make mistakes there. So multiplication, that's quite difficult. Now, say that we have some way, and I'll be a bit more clear in a second how. Say that we have some way to write x as 10 to the power u and y as 10 to the power v. Basically, u and v are the 10 logs of x and y. Now, if you now have x times y, then that becomes 10 to the power u times 10 to the power v. And we have seen that's 10 to the power u plus v. That was one of these properties of powers that I started with. So basically, if you have this here, then you see that if you write that using logarithms, then a multiplication on the left becomes an addition on the right. And that is interesting. So apparently the 10 log of x times y is the 10 log of x times the 10 log of y. And what it basically says here is that you can use logarithms to get from multiplication to addition. And to make that a little bit more clear, I have added a slide this morning that shows what I'm basically doing here. So what I'm doing is I say, well, I have two numbers, x and y, and let's say that they're pretty big integer numbers. And I would like to compute x times y. Now, I can do that. You can multiply these numbers, but that's nobody's favorite pastime. Say that we have an easy way to get from x to its logarithm. So the red arrow here in the picture is the function of taking the 10 log of whatever is there. So here I have x and here I have u, and u is the 10 log of x. I can do the same thing with y. Then if I have these numbers u and v and I add them together, and adding is easier than multiplying. So here I get then u plus v. And if I could now go back and going back, so the red arrow is taking the logarithm, then this, the black arrow, is 10 to the power z. So if I have u plus v and I have an easy way of computing 10 to the power u plus v, then I find x times y. So the idea why you can use logarithm, where you can use logarithms, if you want to multiply these things, first you go down by computing the logarithm, then you do a simple addition, and then you go back. So how can you go from a number to its logarithm or from a logarithm down here to the number? Well, that's what people used slide rules for in the past. So maybe you've seen these things here. This is a slide rule. And you can move the middle part there. And basically what happens is that at one of these entries, say at the top one, you can choose a number. Then you can shift this one and you can read off what the logarithm or the exponential is. So slide rules are a pre-calculator trick or tool to compute logarithms and exponentials. So that's why logarithms have been invented and why they are so useful. So you can do the complicated thing of multiplication, you can easily shift it to addition. Same thing with dividing two numbers. So also division, that's also hard. You can also use logarithms for that. So for that, you have to use a different rule. So here is basically what the slide rule was invented for, multiplying numbers. And then as a special case, if you do that a number of times, if you have x to the power y, you could write that as the log of x times x times x times x, and then use this first rule, and then you see that it's y times the log of x. And if you have to divide, you can write that as the difference of two logarithms. So here you can also see that you can use logarithms to easily compute x over y if you can compute logarithms and do the back step of doing the exponent again. So let me look at a little example where we can use that. Let me check what's coming next. Okay, no, that's something different. So let's see how we can do with that. So let's do a little example from the book. So how can we use these rules? So say that we're being asked, you will get a couple of questions like that, to simplify x to the power 3, y to the power 4 over z to the power 5. Then with these rules, you can express this in terms of the logarithm of x, logarithm of y, and logarithm of z. So I can write this as the ln x to the power 3 y to the power 4 minus the ln z to the power 5. So to do that, I've basically used this last rule here, so that's what we use to get here. Then for the first one, I'm going to write it as ln x to the power 3 plus ln y to the power 4 minus ln z to the power 5. I just copy that. And then finally, if you want to write it in terms of the logarithm of x, logarithm of y, logarithm of z, I can move the exponents in front. So I can also write this as 3 ln x plus 4 ln y minus 5 ln z. So this is the same. If you would have to compute this for certain x, y, z on a calculator, you can use either formula. They're mathematically equivalent. They give the same result. Yeah. Now, I have told you already a couple of times that I have these pictures, graphs of logarithms, exponentials with different bases than e or the ln function. But in fact, you can express everything in terms of e to the power x and ln x. So how can you do that? Well, if you have any exponential function, say b to the power x. So say that we have, I'm going to do this in writing too. Say that we have y is b to the power x, and b can be some different number. Then you can easily see that if I take the ln, so ln y, that is ln b to the power x, we have just seen that you can write the exponent in front of the ln. So this is the same as x ln b. So apparently, I can write y itself, taking the exponential function, e to the power ln y is y. So that's the same as e to the power x times ln b. So now I have rewritten my function. I started with b to the power x, and I've rewritten it as an e to the power something. And the message here is just, well, you can talk about different bases, but you could as well use e as a base. Just rewrite it. Same thing for logarithms. If you have a general logarithm, so here I have y is log b of x. So what that means, it's the inverse of the exponential function. So it means that x is b to the power of y. That's saying the same thing. Now let's take ln's again. So ln x equals ln b to the power of y. I can write the y, the exponent, in front of the ln. So apparently y itself is ln x over ln b. So also if you have a logarithm with a different base than e, you can rewrite it as a function that includes only the ln function. So you could say from a kind of, what shall I say, if you're writing a computer program, as a programmer you would only have to input the e to the power something function and the ln function, and then you can do all exponents and all logarithms. But the reason that it's very, very nice is if you look at derivatives. Because as you may recall, the derivative of e to the power x is e to the power x. And that is why if we're talking about mathematical growth processes where we have exponential growth, that it's very nice to work with e to the power x, because differentiation and also integration is going to be so much easier. So that is the next topic. And to get there, I first want to recall is how we chose e. So we have chosen e such that the tangent line at x equals 0 has slope m is 1. So if you have the function of e to the power x, and at x equals 0, y equals 1, you draw the tangent line, then we know that the slope of that straight line equals 1. Okay? If I write that down, if you have the function e to the power x, then using the definition of derivative at a point, f prime 0, that's the limit of h tending to 0, f0 plus h minus f0 over h. That's when we talked about differentiation. We've used this as definition. So basically we have that this equals 1. Okay, great. Next, if you talk about the derivative in any point, so f prime at a point x, well, this was the definition that we had for the derivative. Plugging in the exponential function, something interesting happens. Because here, since we have that this here is the same as e to the power x times e to the power h, I can write the numerator, I can pull out this e to the power x here, so here's an e to the power x, here's an e to the power x, and I can write that in front of the whole thing, and then take the limit, and this limit here equals 1. So what we have found is that f prime x, the first derivative, equals e to the power x. So it's a very special function, e to the power x. If you differentiate it, you get it back. You get the same function back. And that is why it's very nice to work with if you're doing all kinds of applications in mathematics. It's very easy to have the derivative function. So this is what we have just found. Now, if you would like to compute the derivative of b to the power x, with b possibly different from e, then we can rewrite it. That's what we have just seen. We can rewrite any exponential function in terms of e to the power something. And if you do that, you see that you get this here. So if you use a base different than e and you do differentiation, you can do that, but you get a funny additional constant here. And this constant equals 1 for e to the power x. And this is also one of the reasons why for sine and cosine functions we use radians. Because if we use radians, then you know that if you differentiate sine of x, you get cosine of x. And if you differentiate the cosine, you get minus the sine. If you would be using degrees instead of radians, so instead of 2 pi, you use 360 degrees, you can do that, but then you get a funny constant here. So here comes some constant. Let's call that c. And then you would also get this constant c here, and then with the chain rule you would get an additional constant there too. So that is part of the reason why we use radians for the sine and cosine function, because we don't want all these strange constants. And the very same reason is why we use the exponential function for growth processes, because then if you do differentiation you don't get all these nasty constants there. Now, the ln is the inverse, and if you use that rule, then you see that the derivative of the logarithm of a natural logarithm is 1 over x. If you have a general logarithm, you can rewrite that in terms of ln x, but again you get a funny constant here. Okay. Let me include here one example of this rewriting process. So we have just seen that you can rewrite any logarithm in terms of the ln, and I have one more example. So say that we want to rewrite this thing in terms of the ln. So we have base 7 and we would like to write 12 there. So what we do is the ln of y. No, sorry. I shouldn't be doing that. So what this means is, that's basically using the definition of the logarithm. It means that 7 to the power y equals 12. So y is the number that you should raise 7 to the power to get 12. And now we can take the ln. So then we do ln 7 to the power y equals the ln of 12. I can write the exponent in front of the logarithm. So apparently y equals the ln of 12 over the ln of 7. And then you see that y on a calculator with buttons, you don't need a logarithmic function for every single base, but you can rewrite it in terms of the ln, and then you would just need the ln button there. Okay. Now, one more fun thing here. You know a lot about differentiation, and you know that if you differentiate x to the power 10, that you get 10 times x to the power 9. But what you cannot do yet, where you do not have rules yet, is if you would like to differentiate x to the power x. And I can tell you the rule doesn't hold. So you cannot write this as x times x and then you lower the exponent by 1. So if you want to differentiate this thing, you have to use a trick. And the trick is called logarithmic differentiation. And basically the idea is to get rid of the x in the exponent, because we do not have differentiation rules for an x in the exponent. So let's see how that works. So what we do is we rewrite this expression using e to the power x and ln x. So I am going to take the logarithm on both sides of the equation. So I have this fx is x to the power x. And I'm going to take the logarithm, the ln, on both sides of the equation. So on the left I have the ln fx. And on the right, and that's basically the reason I'm doing this, is ln x to the power x. And we have seen that you can get rid of this exponent. You can write it in front of the ln. So it's x times ln x. And now I'm going to differentiate both this thing and this thing here. So if you differentiate the left side of the equation, you get, well, the derivative of the ln of something is 1 over something, so we get a 1 over fx, and then with the chain rule we get an f prime x. So the whole thing, if you differentiate it, is f prime over f. The right side, well, that's standard, that's just the product rule. So if you differentiate the right side, you differentiate the x, that gives you a 1 times ln x, plus x, and then the derivative of the ln, that's 1 over x. So this is the derivative of the right-hand side. Now I can put them equal because there is an equal sign here, so I can just differentiate and then equal them. So we apparently have that f prime over f is ln x plus 1. And I can rewrite that, and apparently f prime is ln x plus 1 times f. For f, I'm going to plug in the original definition. And apparently the first derivative is this expression here. So the technique that we used here is logarithmic differentiation. That's the name because we use logarithms and rewrite using them. And in general, you can now differentiate anything of this form. So if you have fx to the power gx, you just use this ln and you can write the gx in front of the logarithm. And you can differentiate all types of functions now. So that's great. This is a very neat trick to do that. Okay. So here are a couple of test questions and try to solve them. So the first two are logarithmic differentiation. So use this trick that you want to get rid of the x and you use the logarithm to do that. Here, same thing. And for this thing, this is working with inverse functions. So we have been talking about inverse functions. We have seen the inverse of the tangent function is arctangent. ln and e are also a pair of inverses. Try to solve these. If you cannot manage, let me know and I'll happily answer your questions on Wednesday morning again. Questions about the midterm 2. I'm going to pause here now because we're not quite done for week 5, but I'll manage to do the rest on Wednesday morning. But I'll also happily postpone and first address all the questions you may have. So I will do that. Let me see, there was one more question in the chat. Can we say that 2 ln x is ln x squared? Yes, we can. That holds true. So ln's are great for transforming multiplication into addition. For raising powers, you can just multiply the logarithm by that. And that's the main message of today. As I already said, we've heard a lot about exponential growth, exponential functions in the newspapers these days. It all relates to what we have been talking about today. So today you've learned the mathematics of dealing with that. You know that e to the power x is the natural function for any mathematical growth process, for exponential growth processes. And hopefully you also understand why now, because if you compute the derivative, that is easiest and you don't get additional funny constants if you use e as a base for your exponential function. So now I'll stop for today and please send in your questions and I'll see you again on Wednesday morning. So thank you very much for your attention and until next time.